Okay, welcome to the July 6th edition of the Cosmology discussion group. And Robert French has offered to talk this morning about light and entanglement. And does that sound correct?
Close enough, yeah.
I tried to download your slides, but I don't have Microsoft presentation, so it got kind of messed up. So I hope your slides work.
I hope so, yeah.
Okay. So if you'd ask me to share, I can approve your share request.
Okay, where do I click for that?
That's down at the bottom. There should be a green.
Oh, the green share. Okay. Send request. Okay.
All right, I've allowed it. Okay, now you have to select your presentation from
Okay.
screen that comes up.
Okay, let's see. Just click on the file for it.
Correct. That should work.
Let's see. Do you see it?
No.
You don't see it. Okay.
I don't know. There's something going wrong. Something strange is happening here with my screen. I'm getting um, every time I do Zoom, they change something. It seems to me. And every week there's something fishy happens. It's different.
hmm Yeah, okay. Let's see. Did you okay sharing screen?
Yes, I did.
Okay. What else would I do besides clicking on the file?
Just click on the file, and that should
Oh,
open it.
oh, oh, should I hit share on it?
Yes, you have to.
Hit
Yes,
share again?
you have to do that at
Yes.
the. That's this last step, I think.
Okay, share. And now if I
Still
hit,
nothing.
well, here. Do you see anything now?
No.
Hmm.
All right, let's try it again.
Oh, share on here. Okay, share here.
Oh, there we go. Yay.
Do you see the
Yes.
files?
I see a blank.
Okay,
It
I'll
says
I'll click on
launch.
the file. Okay. How about now?
There it is.
Yeah.
Yay.
Oh, okay, very good.
Yes.
Okay, very good. Yeah. Okay. Yeah, why don't I
All right.
let's
I wanted to mention that I got this book by this woman about entanglement at one of the local church book sales. And I didn't know anything about entanglement. So maybe people who perhaps you'll explain a little bit about that. Uh,
Okay. Entanglement basically means that a function cannot be completely factored. Like you get a cross term, like, oh, if you have x plus y, that whole expression squared, you get a 2xy, which has both terms in it, and that's known as a cross term. And so
correct.
entanglement terms are ones that you can't get rid of, and they have facets from what's going on in very different locations, which sounds kind of paradoxical. My own interest in this actually dates back to when I was a graduate student at Boston University, and among the professors there was Abner Shimoni. He was actually the second reader on my thesis, which didn't have anything to do with entanglement, but he was in both the philosophy and physics departments. And he's actually best known for this inequality, which everyone tests instead of the Bell inequality. It's known as CHSH. Clauser Horn was his graduate student. Clauser got the Nobel Prize. CHS is Shimoni, and Holt is the last one. And I will show that inequality in a bit. Also, my understanding is that originally Shimoni thought that by running an experiment here, it would refute the predictions of quantum mechanics. But when they actually ran the experiments, they all were in accordance with the predictions of quantum mechanics. And Shimoni used to be a realist before this, and then he seemed to give up on realism. He was a bit of a Whiteheadian, so he would say things like that electrons have minds and things. I'm a dualist, but I'm not a Whiteheadian. But in any event, why don't I slowly go through these? I'd like to get most of the.
Before you start,
Yeah, sure.
this is the book, the Age of Entanglement. And
Hmm.
this woman who writes this book, Louisa Gilder, doesn't even mention, she attributes it all to Bell.
Well, the part they actually test is the part that with Shimoni. But
Okay,
Bell was there earlier, and he did have an inequality, but it's different.
okay, well, that's interesting. I'll have to pay attention to that when I work my way through this book.
Sure. Okay, let's see. The next slide. Okay, this is a dilemma for polarization entanglements. This was given by Raymond Chow, who I'm not sure if he's still alive, but he was at Berkeley. And he says that you have two choices. The first choice, which most people seem to opt for, is either give up on the existence of an observation independent quantum physical reality, okay, where things exist independently of our experiences. That's one choice, and people, they talk about propensities and probabilities as being basic, and nothing really, when you even push it, nothing seems to actually come out as actually existing. You never seem to get away from these probabilities. And that's the option that I know, including one of his philosophy graduate students, who actually became head of the Philosophy of Science Association, opted for. So that's the move most people seem to make. But I strongly want to believe in physical realism, that physical objects actually exist apart from our experiences. So the second choice is to allow action at a distance over space-like separations. Now, special relativity fans don't seem to like to think that things can occur over space-like separations. It doesn't bother me. And it also fits in fairly well with my thin shell model because there we have enormous things, these thin shells, at least in principle, they can become enormous. And when one of them becomes collapses, with the absorption process of a photon, then yeah, something can basically instantaneously, a very short period of time, like during the period of absorption, which is like 10 to the minus 8 seconds. Yeah, so I think basically what happens with entanglement is that you have like a joint absorption and the joint process. That's what is responsible for these correlations. Okay, let's see, my
All
next
right.
slide.
Before you go on, space-like separation, that's relativity terminology. That's
That's right,
Minkowski
yes.
terminology. And
That's the terminology Chow uses, yes.
okay, right.
Yeah.
Okay.
Most of these people like special relativity.
Okay.
It's just the truth. But okay, let's see. Next slide. Let's see. Let's see. Maybe I can do it this. Okay, examples of non-realist interpretations of quantum
Okay.
theory.
Bob,
Yeah,
this terminology, non-realist and realism,
yes.
before we proceed, does anybody have want any clarifications about what he's talking about here?
Uh, with respect to the realism, basically it just
Yeah.
means that something physically exists apart from our observing it, that it still exists even when we're not observing. Like you say, an atom exists even if no one's doing an experiment with the atom or anything.
Now, what does non-realist mean?
That it depends upon an observation.
Okay. All right. So that's the idea about Schrodinger's cat. The cat's neither dead nor alive before the
Until
album.
you observe the cat, right? It's in a superposition of being dead and alive at the same time. And whatever, for whatever you can make any sense out of that, you're doing better than I am. And I think you're doing better than Schrodinger did because he thought it actually was a counterexample of the quantum mechanics. He did not like the Born interpretation of quantum mechanics.
Okay.
Okay, but here are a few quotes. No phenomenon is a phenomenon until it is an observed phenomenon, from John Wheeler. Uh, Quantum correlations exist without correlata. So you have the correlation, but you don't have the things existing which are being correlated. That's David Merman, the ethical interpretation of quantum mechanics. And yeah, so Merman, he's well known. He was at Cornell. Quantum information exists without a medium carrying the information. Anton Zeilinger, who shared in the Nobel Prize. I don't know, maybe Shimoni would have shared in it also, except he'd already died. Or Richard Feynman, do not ask how it can be like that. Yeah, they just want to make like predictions and do run experiments, but as for anything basic existing responsible for anything that you want to say is nonsensical or that it's not really there or is meaningless. Different people say somewhat different things.
Okay. Is this fall under the Copenhagen?
Yeah, that's Copenhagen. Yeah.
Okay.
Niels
So these
Bohr.
are
The later
papers.
Niels Bohr. I like the young Niels Bohr. I don't like the later Niels Bohr.
Okay. So this would be Copenhagen, which interpretation, which is kind of the official version.
Yeah, yeah. There are other ones out there, but yeah, probably it's the biggest.
Okay.
Yeah. Okay, let's see. Next slide.
This is kind of, just to comment on these ideas. I mean, they don't seem to be really, um, they, it's it's kind of hard to really make sense out of what these interpretations are trying to do.
Well, they think they're forced into it. And among the reasons they think they're forced into it is that if you make this other move for non-locality, that seems to conflict with special relativity, and they love special relativity. I don't, but they do.
Okay, that's interesting. All right, so we got a disconnect with special relativity if you want to believe in it.
Yeah, well, the way Shimoni talks about trying to save special relativity is that you can't use these correlations to send information or to send a signal. There's causality occurring faster than the speed of light, but you can't use it for sending a signal. And why that's
Right.
relevant is little bit beyond me. Uh, or he talks about like events being actualized in tandem. So it's just potentiality before that. Or he talks about peaceful coexistence between special relativity and quantum mechanics, which makes it sound political. Maybe it is political. Okay, well, in any event, my next slide. Reasons to seriously consider non-local explanations of entanglement experiments. There's a lot to be said in favor of a physically realist version of the causal theory of perception. In other words, what's causing us to like have the visual experiences that we do is like the passage of light rays, and there's at least a mirroring of structure between a distal object and the experience, which is linked by light rays and various things happening in the brain. Okay, I think that explains an awful lot. Secondly, physically realist theories should be at least logically consistent, but beyond that, almost anything can be questioned, including questioning special relativity. You do want logical consistency, but I don't know as we want any other restraints. And certainly I don't want restraints from relativity here. Thus, non-local realistic models of the physical world deserve investigation, even if they tread on certain generally held fundamental assumptions of modern physics, including the Copenhagen interpretation of quantum mechanics and non-epistemic. Epistemic means knowledge, so you say it's not just concerned with knowledge, interpretations of the special theory of relativity. Okay, we do want consistency, but to my mind, everything else can be questioned.
Okay, so the
Just a point here, if I may. On the one hand, you have the sort of special relativistic um, uh, system where nothing can exceed the speed of light.
Right,
On the other hand, you have the local explanation of entanglement, where you
right.
have sort of like an instantaneous reaction. But couldn't you have something in between? You might have a reaction which actually is not instantaneous. It doesn't have infinite speed, but it travels at, maybe orders of magnitude greater than the speed of light. So, for example, one can formulate a gravitational theory of that nature.
You could try something like that. You have to get it consistent with the results of some of these entanglement experiments. Where, as far as I can see, you're dealing with certainly very short periods of time, like the time period for absorption, which is something like 10 to the minus 8 seconds, over like for some of these experiments. I know the Chinese, they even have a satellite up there, and they send an entangled light up to the satellite and back down, and they get the correlations.
Okay.
Okay,
Uh,
let's see.
Can I
Next.
just
Bob,
uh,
what do you mean by
oh, sorry.
non-epistemic interpretation
No,
of
okay.
special relativity?
Epistemology is the study of knowledge.
So
So,
non-knowledge interpretation, what are you
yeah. So,
talking
in other
about?
words, in terms of something existing and not just our knowledge of it.
In other words, a realistic view.
Right, which I hold.
Thank you.
Yeah, okay.
James.
The there is one other interpretation I've seen, and I don't think he's taken that seriously, but he's done experiments with gamma rays which have a longer absorption, and he thinks there's a continuous absorption and a quantum emission. So there's an asymmetry between so that it's almost like there's some part of the absorption that can happen without an emission, and so you can get preload. The Anyway, his name is Eric Rita. He's got some results online with gamma ray.
Yeah, I think I've
Yeah,
heard something a little bit similar with advanced waves, and I know like there was a while Feynman and Wheeler were playing around with something a little bit similar, that it's a joint sort of process between the absorber and the emitter. I
yeah, the
have run across
continuous to
that
the
before.
yeah. So you have all right. So that is a third. It's undeveloped, but it's a third.
Eric
Yeah.
has
Well,
presented.
if I may, the Eric Ritter data, I think, is actually showing that there's something already there aside from what we might call perfect vacuum or empty space. In other words, I think Reader has shown that there's something actually there to account for his results.
That's possible. Yeah.
Right.
Okay, before we
Okay.
go off of here, I want to mention that Eric has given a number of presentations for the CNPS, and I think you can look those up
Mhm.
um, on the CNPS YouTube channel.
And he is in touch with us periodically. In fact, Dennis Allen is at the moment in correspondence with him about some aspects. So he is around still.
Okay, okay, Bob.
Okay, next slide. Okay, I don't like dualities. I like unities. Bohr was big into the wave particle duality. It turns out I met him back I went to a conference at UMBC, University of Maryland, Baltimore County. Yanhil Shi invited me there, and it was sponsored by the Defense Department. But among the people there was you sign Yilmaz, and he has this concept of wave particle unity. His versions are somewhat different than mine, but basically we both end up talking about wave packets. And so you have electromagnetic wave packets and like oscillating waves within the wave packets. Uh, so the concept, I'll just read through this, is wave particles, okay, are construed as being spread out over all physically possible paths. Feynman talks about light taking all possible paths in his little book, QED. As far as I can see, you can get the same results if you constrain it to just physically possible paths. Uh, but still, a lot of funny things happen between the emission of a photon and its absorption. And then I've gone over this with some of my other presentations with my thin shells. Wave particles glide past each other in separate parallel subspaces. Okay, so there's a superposition. It's only once you get a potential absorber involved that light just doesn't go past light. Also, I have these broken up and recombined. Wave particles can be broken up into partial particles when elastic scattering occurs. For example, I think this happens in the reflection of light from a mirror. And Feynman points this out. It doesn't occur just at one point on the mirror, it occurs all over the mirror. But for most locations, you get destructive interference, but where you get constructive interference, it's just paths close to the classical path. Next, densities of wave particles increase in other directions when not absorbed by a potential absorber. Like a good example here is the formation of a shadow. There's no light behind the object blocking the light, but it's not absorbed either. But it looks like ignorance. You say, well, the light never hit it there. It went in a different direction. Under my account, it was there, but it got pushed aside. And this is known as the Renninger effect, which I think is a genuine effect. It turns out that you can account for this in terms of just being pushed aside. There's no other differences besides an increase in probability of absorption in other directions. And there actually are experiments. Paul Quioid, he had an article in, I think Scientific American called Seeing in the Dark, where the net results is that what's not absorbed, but could be absorbed, it actually changes the predictions. And then I say a traveling wave particle which travels through a medium is a coherent concept. I guess I've mentioned this before, but I still do hold a version of an emission theory, but it's not a very traditional version. It's not Ritz's, it's not a ballistic version, but I have charged particles carrying their fields with them in these parallel subspaces. So light still has a medium, it's just each particle carries its own medium. There isn't one medium that carries light from different particles.
How do you define the parallel subspace, Bob?
Well, just the way it's usually easiest to visualize with fewer dimensions, but think of like straight lines drawn parallel to each other, like on a piece of paper. They don't touch each other, but you could have in principle an infinite number of them. So I have a large number. I have one of these for each charged particle in the universe, which the best estimate I've seen of is something like 10 to the 80th. So there's a lot of these, and they're in order, but they don't literally touch each other. And I hold that they can't interact unless there's something that goes through the whole group, which is what I think a charged particle does. Okay, it may sound a little bit odd. It's the only way I've been able to get things to work. The universe, I'm satisfied no matter how you construe it. If you're going to account for some of these experiments, it has to be pretty odd. But I do want to retain realism. And I'm willing to say some pretty odd things in order to retain realism. Okay, let's see. Here, this interferometer. The initial experiments didn't actually involve what's known as parametric down conversion. But Yan Hao-Shi, with his at the University of Maryland, he created the Shi Alley interferometer. It's always called HOM for Hong, O, and Mandel, and he explained it to me. He actually showed Hong and O how to do this, but their version got published first, so they got their name on the interferometer. Okay, but in any event, you put laser light through what's known as a nonlinear crystal. The usual one that's used is one that was developed in China, BBO, barium borate, and it turns a very small percentage of the photons, something like 1 in a million, into 2 photons. There are 2 types. There's type 1 and type 2. I showed just type 1 here. where both photons come out with the same polarization. Uh, Also, one usually has a higher energy, that's known as the signal. The lower energy one is known as the idler. So you have conservation of energy. You also have conservation of linear momentum. So if one they go off to the side, but the second one goes off in a way so that the net total momentum would go straight through. Okay, then for type 1, you have to get different polarization. So you use a half wave plate to change vertical to a horizontal polarization. And then you put both of these through a beam splitter, the non-polarizing beam splitter. So note before then, you have the light separate, but both the horizontal and the polarized light is sent to each of the detectors, and first goes through a polarizer, and then the two, you count them together with a coincidence counter, which just clicks when both occur at the same time, both that are detected at the same time. Okay. And if you do this at the individual detectors, this is known as counting singles. The sine squared, the cosine square, that is off of Malice's law. I don't know if people know of Malice's law, but with polarized light, the intensity is a function of the cosine squared of the angle. Uh, so basically, sine squared plus cosine squared, of course, equals 1. So the total is going to always be the same if you just have talking about at one detector. However, when you talk about at both detectors, that's with the coincidence counting, and there you get sines of one times cosine of the other, plus or minus sine of the second times the cosine of the other, which equals sine squared of theta 1 plus or minus theta 2. Yeah, and that's off of, you can find this in a book on trigonometry. The sine of theta 1 plus or minus theta 2 is sine of theta 1 times cosine theta 2 plus or minus sine of theta 2 times cosine of theta 1. Okay. And off of this, you can get the CH-SH inequality, which is what I have next. Yeah. So, yeah, here are the correlations. So these are the different angles. It's always the difference between the directions of the two polarizers. Uh, so you can, basically they do is they turn one a little bit beyond like either being straight horizontal or straight vertical by like 22.5 degrees. And then you slowly turn the other one to these different positions. And if that's the case, we have those positions for A, B, A prime, and B prime. And the inequality, this is the CH-SH inequality, not Bell's original one. But for those AB, the angle AB, A prime B plus A prime B prime minus AB prime is going to be less than 2. And the quantum mechanical prediction is it's 2 times the square root of 2. And every time they've done this, or essentially every time, the results have been in accordance with the quantum mechanical prediction. And they say that this shows that any local hidden variable theory is not going to work. And I think they're right there. A local hidden variable theory is not going to work. Yeah, I think it was von Neumann, like who maybe first talked about hidden variables. In other words, that there's more going on than we can observe. And these are the hidden variables. But no matter how you do your local hidden variables, in other words, what's just right next to something in the local part, nothing going faster than the speed of light or anything, then you can't account for these inequalities. Okay, so those are the EPR inequalities. And let's see, next I have my way of trying to explain this with advanced waves. I do it first for probability amplitudes. Now it's interesting in quantum mechanics, like psi is a probability amplitude, but it's not itself a probability. You have to multiply psi by its complex conjugate, psi, in order to actually generate a probability. And as far as I can see, forces are like, or force fields, they're like the probability amplitudes. Energy, and of course, those are vectors, whereas energy, which is a scalar, that's itself a probability, and a probability per se is also a scalar. Okay, so in any event, I have my polarizers behind my detectors. And so notice that when the light from the beam splitter goes through the polarizers, we get combination terms here. Uh, and here's where I bring in advanced waves, which goes from one detector, as far as I can see, basically back to the crystal and over through the other detector and through the polarizers. When you bring in these advanced waves, then you get those terms, cosine sine of theta 1, sine theta 2, and sine theta 2, cosine theta 1. And those are the terms which have both polarizers, angles of both polarizers in them. So those are the entangled terms. And it turns out those are the exact terms which you have in that equation for the CH-SH inequality. So those are the entangled terms which cannot be factored. So I do this first for force fields or probability amplitudes. And then I also do it for the advanced waves for energy fields, because I have to say that when absorption occurs, and the odds for absorption are determined by these probabilities, the actual energy is actually yanked from one location, I don't know, backwards through the crystal or something, over to the other detector. So everything is discrete. You get the whole thing, and it has a definite angle of polarization when it is measured. But the equation for it includes that cross term, which cannot be factored. So, and the way I consider these advanced waves, I'm going to have another slide on this later. But some people, they talk about advanced waves as something going backwards in time and then going forwards in
Yeah.
time, like going backwards in time to an emitter and then forwards in time. I don't particularly care for things going backwards in time. Who knows? I suppose it's logically consistent. I don't find it very intuitive. But my concept was to say, well, maybe something occurs very fast. This whole process occurs very fast during a moment of time without anything going backwards in time. Which I
Okay,
think
Bob, is this kind of like tachyons? Do they go forwards or backwards in time?
they go faster than the speed of light in theory. I don't know, as anyone says, tachyons go backwards in time. There are people who talk about things going backwards in time, but
Yeah, I've heard
tachyons,
about this, but it's not clear to me what
yeah.
that
They
means.
might talk about things like a positron being an electron going backwards in time.
Yeah, yeah, okay. Yeah, this may be. I do know some physicists do talk about things going backwards in time. And whether it's just a figure of speech or whether they mean it literally, I think people vary. Okay, but it would explain the correlations, which I think interesting.
The coincidence counter, does it have to be set below a certain window of time? And if you have it greater, you lose the effect. Is that
Yes, yes, it's a very short period of time. Yes.
a very short period?
Yeah, yeah. And I tried to get she interested in running an experiment testing this, but kind of like blocking things after light went past, after it was emitted, after it went past the crystal, but before it reached the detector, blocking it. And his way for trying to do this was, excuse me, with a Pockle cell, which changes the angle of polarization of light. And some of these are pretty fast Pockle cells. Like you can drive them at around like 100 kilohertz. And for a long time, we tried to get this. I even helped him buy some equipment to do it, and then he had various problems. But eventually, he was actually nice enough because he had a number of Chinese graduate students, and I guess it's 3 years ago now. They actually did it in China. And I'll show you the results.
Are you talking about creating a window which ignores the very fastest window and gradually creates a window that's moved longer and longer intervals? Have a maximum time and a minimum time.
Yeah, okay. In the minimum time, yeah, it is very short. Let's see. My screen's partly blocked here, but do you see the correlation in the second one? The peak?
Yeah.
Okay. Okay, so that's the unblocked correlation, shows a peak. Blocked shows no peak. And this is the experimental result which they had in China. Which, on the surface looks interesting. She says it doesn't actually support my theory. If anyone's interested in getting into this, if you like, if you like, I can read the email that he sent me on this.
Well, maybe later.
Oh, okay,
Yeah.
maybe later. Okay.
We're coming up to 3 minutes. We got 3 minutes.
Okay. Well, maybe we should. Well, maybe people have questions here. Either way.
Well, just getting back quickly to a point you made earlier, Bob, you said that you adopt some sort of emission theory,
Yes.
but you're not Ritzian. Would you accept something which is similar to Ed Dowdy's ideas?
Yeah, I knew Ed Dowdy very well. Yeah, and he was quite interested in my position. Yeah, but I was never entirely clear whether his version was ballistic or not. He knew a lot of people. Yeah, and actually, he was with me in talking with Xi a number of times. Because he was at Goddard, and UMBC is not all that far from Goddard.
Oh, okay.
They wanted to run some experiments at one point, and Goddard was going to help them out, and nothing really came of it. But
So she is at UMBC.
yeah, as far as I know, he's still there. I checked today. I mean, he's about my age, but
So he's not retired yet, or
yeah, I thought maybe he would be. But I checked the UMBC website today, and he was still listed as active faculty.
okay. All right, we got 2 minutes.
Yeah.
Little under 2 minutes. Now so the expectation is that when it's blocked, there's no correlation and there's nothing there, right?
I guess I find it confusing to tell you the truth. But I guess what he's saying is that when it's blocked, my prediction would be there wouldn't be a correlation, and this shows a correlation. But I still find it confusing. You would think with an experiment that for the two cases you would expect different results. And
Well, I mean, the unblocked has something on the spike on the right hand side, right?
yeah. Well, he admits that there's a spike, but he still tries to explain it as not supporting my position.
Okay, but there is a difference. I mean,
There's definitely a difference there. Yes.
one shows a spike and the other one
The
shows
other does not. I think we all agree on that. Yes. The question is how to interpret this. To me,
So
it
we're
is
back.
interesting that there's a difference. Yes.
So it's all about how you interpret what you did in your experiment.
Yes, I agree.
Okay, so we should be cutting off here in a few seconds. Anybody else have any questions before we start the next session?
Do we move to a different link now? Do we?
Yes.
I haven't done this before. It's the other links on the email. All right.
Yes, the second link.
Second link, yeah.
By the way, I was speaking to James and also Jeff, our presenter, yesterday, and I invited them both to the talk today. James.
Let's see. Do I have to open the slides again?
Yeah, you have to do the whole. I think you have to do the procedure again. I'm not sure where. I don't think it remembers.
Okay. I can try hitting share and see if that does it. Sharing is not turned on. Maybe you have to send a request. You can
No,
request.
you have to. There we go.
Okay.
There we go. Okay, now you have to click on the presentation and then click share screen.
Okay, let's see. Click on presentation. And then
While this
share.
is going on, I might mention, uh, I was asked for a password, and you might want to, Harry, publish along with each session what the password is, because some people without the password were unable to enter. What I did is I had to restart over and re-click the link, but it might be useful just to have the password for each BE meeting.
All right, well, Zoom is already complicated.
Okay, let me see if I can get this to, okay, PowerPoint. Let's see. Did that work?
Not yet. You have to click the share screen. You have to click the share.
The share, okay.
There we go.
Okay. It's there?
Yes.
Okay, you can see it. Let's see this.
I'm not seeing the presentation. You need to click on the file for your presentation.
Okay, there's the file for do you see it now?
Yep.
Oh, okay, good. Okay. Let's see. Okay, so we did the experimental results. Okay, here's my next one. Let's see if I can get this to move through. Ew. Okay. Yeah, here's my concept of an electromagnetic field. The traditional concept is when there's one field in space, charge effects are added from each charged particle so as to create a single field. The resultant force is given by the strength of the field at a given location. But my version, each charged particle has its own field in a separate parallel subspace, and the resultant force is given by the vector summation or superposition of the fields at a given location, and this is used to explain interference effects. It basically, the predictions are the same, but it's just a question of where you do the summation. So, for example, with an electric field, I hold that there are electric fields, very strong ones all over the place, but usually they cancel each other out because atoms are electrically neutral. But the fields, both the positive and the negative ones, they're still there, but the effects just cancel out. And as far as I can see, that actually works out. Okay, so that's my concept of the electromagnetic field. Then let's see. Oh, this is what's going on here. Okay, here's my way of my thin shells. I have them rotating. So probability amplitudes are identified with rotational waves, in other words, with force fields. And the probability of absorption, the P here, is given by adding the two kernels, K and K1, okay, where both of those involve summations from these probability amplitudes. And this is identified with energy density fields. So probability amplitudes, those are the forces, and the actual probabilities, those correspond with the energy density fields. And you have these like going in different directions for destructive interference and together for constructive interference. Okay, so those are the rotational waves. Next, let's see the probability paths, amplitudes for paths, and this corresponds again with Feynman's summation over all possible paths. Okay, A here is a normalization factor, and I give it there. And the width of a wave packet is the width during the time of emission of light, which is, again is usually around 10 to the minus 8 seconds. And the probability for a single path is the 5. We have both here. You have, and I kind of want to tie this into like an electric field and a magnetic field because light's electromagnetic. So phi 1, maybe that's the electric field, and phi 2, the magnetic field. And you sum the two, and this will give you your actual probability. So you can have either constructive or destructive interference off of this. Then let's see. Here's my uh, how I account for light being propagated within a shell. Uh, and I have added dimensions here, but basically it goes from one thin shell, and when the positive and negative, I identify those with perfect or ideal liquids. They oscillate back and forth, and it pushes it up a step each time. And I would say that this occurs at the speed of light. So it gets passed from shell to shell at the speed of light. And basically, these shells are the medium for propagating light. Then I have one for polarization. I use the Poincare sphere. So you have circular polarization, either clockwise or counterclockwise. At the two poles, you have elliptical at an angle in between, and then you can have either vertical or horizontal along the equator. And then I say polarizers don't filter light, but act as new sources. If you want a nice experiment to show this, you can actually have light go through a vertical polarizer and then a horizontal polarizer, and no light goes through. But if in between those two polarizers you insert one at an angle, say 45 degrees, then all of a sudden light appears beyond the second polarizer. And as far as I can see, the only way you can explain that is the polarizers aren't actually filtering light, but they can, in effect, constitute new sources. Then I have one for the effect of a beam splitter. Under the traditional way of quantum mechanics of looking at this, the wave that is split at a beam splitter is a probability wave. And particles are not split. They are either the whole particle goes one way or not, or the other, but it's probabilities. That's where you get interference effects. It's from the probability wave going in all possible paths, but not actually the particle. The particle remains small. The way Yilmaz had this going with his wave particle unity, he thought the whole particle with the probability either goes one way or the other. It doesn't split. But I hold both are split. Uh, so if both are split, then you have something separated and then recombined. But I think what becomes recombined can have a new source. But emission is always discrete, absorption is always discrete, and you only get interference when everything has the same wavelength. But in spite of all of this, you can have this, like with elastic scattering, you can have like things being split apart and recombined from other sources. And hence you have non-local collapses of a spread out wave particle. And I think that's what occurs during these entanglement experiments. Okay, let's see my next one. Reasons EPR correlations require a special reference frame. I don't know if people have heard of Elaine Aspect. He also shared in the Nobel Prize, and he was the first one to show that with space-like separations, you still get the EPR correlations. And then there's this book by Tim Maudlin, and he likes relativity, but even he says causation travels faster than the speed of light. Information travels faster than the speed of light, but the information cannot be used to send a signal faster than light, and that's his way of saving special relativity. There's an awful lot of politics involved in this. I mean, people just refuse to go along with a conclusion that something's actually occurring faster than the speed of light here. And as far as I can see, the real motivation is they want to save special relativity. Let's see my next one. Role of special reference frames in polarization and entanglement experiments. So you need them in order to explain the results of aspects experiments. Also, Gisson, he's at Geneva. He's done a number of experiments with sending down converted light through optical cables. And even his sometimes like they're kilometers in length. And he's had some with moving detectors, like rotating detector and things, and moving beam splitters with an optical switch is a very fast one, and he always gets these correlations. So you need a special reference frame to account for all of that. And of course, the special reference frame, again, as far as I see, goes against special relativity, and that doesn't bother me. I think we have these special reference frames. For me, it's like the special reference frame, say, of an emitting particle, the source particle. That's a special reference frame, and it has its own set of fields, its field with it that moves with it. So that's a special reference frame. But there isn't just one special reference frame. Each source particle is going to have its own special reference frame. Okay. Let's see, I have one, advanced waves. The traditional ones, they kind of talk about backwards in time. Even this David Klitschko, he says, and he was accounting for what she did is experiments with imaging. It's known as ghost imaging, and you do it with down-converted light, and you pass the down-converted light through like a screen that has various holes in it. And the image which you get with coincidence counting is always twice as big as it would be under normal optics. Yeah, and Klitschko said that you could explain this if light went back to the crystal and over to the other detector, then that would make it be twice as big since the path light length is twice as long. And with his version, he talks about going backwards in time. But of course, with my version, I try to have the whole thing occur in the present, but in a very short period of time. Yeah, then Wheeler and Feynman, they also had a similar concept going, advanced potentials, where they say that emission and absorption is just one event, not two, and they invoke advanced waves here. And of course, for my advanced waves, they have to be affected by a polarizer, or I just won't get the results I need. And again, that sounds strange, but it's logically consistent. And let's see. Okay, explanation of EPR correlations by an emission theory. Okay, this is actually the Schrodinger cat paper. As Schrodinger notes, quantum collapses require an absolute time. That didn't bother Schrodinger. Okay, for space-like separations of detection events, this requires a special reference frame. Okay, the quantum interference term, that's the cross term here, the one in the middle, 2 times sine theta 1, cosine theta 1 sine theta 2, cosine theta 2. It cannot be factored into terms for each detector individually. Okay, she has a paper showing that. The interference term equals sine squared. Again, that's from that trigonometric equality, plus or minus theta 2, and can be measured by coincidence counts by changing the angle of one polarizer while keeping the other fixed. And with correlated 2-photon absorption, each detection event draws energy from both sets of energy fields. So it's not all there at either detector individually. It has to draw from what's present at the other detector in this very short period of time. Yeah, you look with the coincidence counts, like with the experiment I showed you with Xi, yeah, it's like 10 to the milliseconds at least. It's even shorter, maybe 10 to the minus 8 seconds. It's a very short period of time that you actually get the correlation peak. And then here's the traditional account. I don't completely understand it. So, but they do bring in these Glauber correlation functions, where the E minus and E plus, they are respectively creation and annihilation operators of the electric field. Coincidence counts. Here you bring in a tensor product between the two and a projection operator. So the probability here, e to the I, brings in complex numbers where alpha and beta are phases associated with 2 alternative paths for the signal and either photons, and where Q1 here is, or Qi is the projection operator onto the new polarization axis. And this equals sine squared. And so they do get the result. I don't know. I kind of prefer my own explanation. And this isn't physically realist either. It has complex numbers and any number of things. And I don't know as you can avoid the complex numbers with them. I do everything I possibly can to try to avoid complex numbers because it's not clear to me how something a complex number or an imaginary number can actually refer to something physically existing. I can see how it could be part of a calculating device, but I don't see how it can correspond to something physically existing. And let's
Well,
see.
the complex number may simply represent that a particular phenomena has two components.
Possibly. I've seen various people try to minimize the imaginary part of them, but to me, as far as I can see, they're basically used like with the probability amplitudes. One of those could be complex, but you only find something that you measure with the whole probability, which is multiplying one probability amplitude by its complex conjugate. Uh, yeah, well, in any event, that's the end of my presentation. We can go back to any slides, particular slides anyone wants to, or be happy to try to answer questions if I'm able to.
You mentioned about different paths, about sending light down. Did you say a fiber optic or other things?
Gislin's one does involve fiber optics, yes, and they even send it between different Swiss cities and things.
So, doesn't the theory of how light is transmitted in glass or another thing come into it? Because
I agree, it comes into it, and glass, light through glass, my understanding is slower than light in a vacuum. Nevertheless, it retains angles of polarization, and evidently they still get these quantum correlations when they do it.
So the typical it's altogether not clear to me how light is slowed in glass, but there is a sort of interaction effect according to the mainstream view that with electrons. So here's some sort of interaction, but there's no scattering, there's no like quantum scattering or anything like that.
Yeah,
so how do you
An
understand
awful
it?
lot is preserved, and why exactly it is preserved. Those are good questions that I don't really have good answers to. I'm not an expert on how light goes through an optical fiber. I know that they're used all over the place, like with in communications these days, and you'd have to ask an expert on it.
And if you just one question,
Sure.
if you have a laser with a exactly defined polarization rather than a polarizer creating a sort of a sine squared distribution, if you rotate the fiber optic, can you rotate the precise angle of the output polarization?
Again, a good question. I'm not certain on the answer to that. So you want to put a twist in the fiber and
Yeah.
see whether that rotates the light or not. I hate to give answers when I'm not certain of the answers.
Okay.
Okay, nobody else seems
This is a
to.
question.
Well, let's see.
I'm
Go
I'm
ahead.
sorry.
Oh.
Okay, let me ask you the question. What kind of beams used in all these experiments? Laser beams or which one?
Laser beams. The initial ones were using CW, continuous wave, and an awful lot has also been done with pulsed lasers.
Laser, what kind of laser? I mean, wavelengths, coherence of the beams. Somebody measured coherence of what?
Okay, the ones I used, and I worked with someone for a while. He was initially at Wayne State. He was actually in the chemistry department, then at the University of Michigan. They were using 800 nanometer light, and then you would use SHG, second harmonic generation, and that they would, but it was the 800 that they would put through the down conversion crystal. No, excuse me, the SHG through the down conversion crystal, and then you'd have the 800 again coming out with the down converted light. And that was a pulsed laser.
100, which one? Because I don't know about 800 nanometers pulse laser. Diode lasers, they are close to 800 nanometers. I'm sorry, I'm an optical guy. All my life, I worked with lasers, with beams, with all this stuff. That's why I have a lot of questions about the quality of the beams. Not you personally, but it was used in these experiments.
Okay, as I was saying, The initial ones use CW lasers. I don't have the information right in front of me. I think it was around 600 nanometers. And I do know the pulsed ones, almost all of them seem to use 400 nanometer as the input, and then you get the signal in idler. And usually you actually want them at the same wavelength, but they come out at different wavelengths also.
It was pulsed with. What is the duration of the pulses used in this experiment? Nanoseconds, picoseconds, whatever.
Even
What kind of
100,
laser beams? You know, it's
femtosecond.
very important for
Yeah,
these
yeah,
experiments.
yeah, 100 femtosecond pulses.
100 femtosecond, unbelievable. Okay, then you cannot use continuously working lasers because you know you must have a high power to
I
have
know
this
they've done both.
femtosecond.
They've done it both ways. They've done it with CW. The ones I was using that was with pulse, and it's fast pulses, 100 femtosecond. She's done it with both types of lasers, both with CW and with pulsed.
Okay. And what about coherence?
Titanium
Do
sapphire.
they have this, parameter, coherence? Because this, correlations depends on the coherence of the beam.
Yeah.
And on the source, how it worked, better correlation between photons, you have higher coherence.
Yes. That's constructive interference. Everything's in phase with coherence, yes.
Do you mean
somebody measured coherence, because coherence you can measure with this, combinations, with correlation between them. The same idea I used 50 years ago.
Sure.
By the way, this.
Yeah, but the pulsed one, this helps you at all. That was a titanium sapphire laser.
Pardon me.
Okay. Let me ask you another question. What about the optical quality of all these optics? Because there are no ideal optics. All your calculations, everything based on the 100% quality of these optics. Never you have this. Never.
Well, I mean, you're absolutely right, and it's a little bit tricky setting this up. And my own background, even though I did work with this chemist, my own background's in philosophy, and so I'll be
Okay.
I always want someone else working with me on something like this. Some of the people I worked with seem to be very skilled at it.
Yeah, I had so many questions. I'm sorry,
No, it's
because
okay.
I know something about the optics and laser optics. I started my education at lab of Alexander Prokhorov. He was Nobel Prize laureate in physics, in lasers particularly. That's why I have very good experience, and I have so many questions to
What university
experiments.
what university was that at?
My university was Moscow Physical Technical Institute, and I worked in his lab for 7 years. That's why I know something about it. I saw even the first laser in his lab.
This David Klitschko, who also came to America, he was in Moscow, I think at Moscow State University.
No, it's not. It's a different school, but it does matter. What does matter, where he worked. I mean, in what lab, under leadership of whom, and so on and so. Everything depends on school. And I passed very good school with Prokhorov, That's why I have so many questions. By the way, I was very excited when I was a student about the coherence of the optic of the beams. And what is important, coherence depends on these correlations between two detectors. I wanted to go with PhD in this area at that time. But what I'm hearing today, I don't know. Sorry, even for my knowledge, it was impossible to understand what is going on with these ideal graphs, these figures, and all this stuff. I am a real guy with the real beams, with all the lasers continuously running, pulsar running from UV to infrared radiation. That's why, all solid state lasers I passed in Russia and in America for 29 years. And I know the quality, optical quality of these, optics you use and all the guys use. It's very difficult to have a very good optics.
Yeah, this down conversion was originally developed in Russia.
Look, optics in America much better than in Russia, believe me.
Yeah, no, I have a lot of admiration for what they do in Russia in science.
Yes, the science is good, but optics not so good. It was,
Maybe.
especially in 80s, 90s.
Yeah.
Forget it.
Yeah. Yeah.
Okay, anybody
That's
else?
why, guys, I'm very confused with all these results because I don't believe in ideal optics. I don't believe in an ideal coherence of the optics and so on and so on. I don't believe it,
Well,
because
here's
I
the
know the real life.
Yeah, I know. The real one, I mean, you try to get it as good as you can, and evidently they're able to get it good enough to measure these correlations. Nothing's perfect. Uh,
I'm sorry for my, understanding what you're talking. It's a very good presentation. Never I heard about it. I don't believe really in this one because there is no 100% reliability of these results
well, I
because of
mean, you get
coherence
some
of the
noise
optics.
in anything, but they've done any number of I don't know how many labs they do it in now. They even do it in undergraduate labs now.
In view of what Vladimir is saying, um, is do these publications that you're citing, Robert, um, include the statistical analysis of the data, by which I mean standard errors?
Uh, well, here's what. As far as I can see, the answer is definitely yes. And I'm not a statistician, so it's not that I've analyzed it, but yeah, I mean, there are definitely reputable people doing these.
So
And
that
as
means
I said, they even gave a Nobel
they're
Prize on this.
using t-tests or whatever to establish that a difference exists that's
Uh,
random.
well,
Again, given the variations possible in Vladimir's comments, that's why I'm asking, if the data you're citing includes this statistical analysis of variability and whether there actually is a signal there or not.
well, certainly it's repeatable. And certainly the people doing these, I mean, yeah, they routinely do statistical analysis. But again, on more details, I just have to admit ignorance there. I can
Oh,
give you
okay.
any number
Well,
of references on this, but
you've addressed my question. Thanks. Yeah.
okay.
But haven't these experiments been done with other types with electrons and other particles?
That's a real good question.
don't think so.
I've heard even like things with whole atoms, and then doing superpositions of atoms, and so it's been a little while since I've actually been looking at this actively. But it seems to me that yeah, that they have been doing some of this with other particles. The only part I really know anything about is with light and using lasers. But it seems to be something, I mean, I've heard any number of people try to just dismiss the results, and I think that's the wrong move. I accept the results. I just don't like the anti-realism that seems to go with a lot of accounts behind them. But if that's the case, I do think you need something non-local. And being non-local, like a non-local or global hidden variable theory, I think that's probably what we have to go with. And I don't see a problem with that.
Okay,
And that doesn't go along with special relativity. So much the worse for special relativity is my attitude.
we have a number of different issues here. One is by what you're referring to as the Copenhagen by non-realism or the non-realistic. You're referring to the Copenhagen concept, correct?
Usually, there are about 10 different interpretations of quantum mechanics out there. There's many worlds. There's David Bohm's one. There are a whole bunch. Copenhagen, I mean, there it just talks, it's kind of ties in with the positivist philosophy of science. Everything's about what you measure. Or Bohr, he talked about phenomenon, and it's a different way than philosophers talk about a phenomena because he means something physical, but at least has to be macroscopic. So like maybe if you photograph it, then it's a phenomenon. You don't need a mind there, a conscious mind, in order to photograph something. But or maybe once you can register it in a computer or something, then it's a phenomenon. But if it's something that you can't measure, then yeah, they kind of say it's meaningless. They tie this in with various philosophies of science that just stress something being, if it can be verified, then it's meaningful, otherwise meaningless, things like that.
The fact that so many different interpretations are possible indicates perhaps that the theory being interpreted is really not specific enough and is faulty and incomplete.
If you say it's
Hidden variable
incomplete, then you're
idea.
talking about a hidden variable theory as being more complete. But I think you are forced into global hidden variable theories and not just local ones.
Have you followed up? Oh, sorry.
Okay. Let's see.
Have you followed up the theory of the two photon emission? Because that's not typically quantum mechanical, is it? So when whether one photon would be where one photon would normally be emitted, there's two identical
That's right.
photons
Yeah.
or a different.
Yeah, that's the way down conversion works. Yeah, and they call it ghost imaging. There's a little more to the story here. People know about Karl Popper. He's a philosopher of science, a pretty well-known one.
Yeah.
Well, he had an experiment. Actually, he had a correspondence with Einstein on about with paired light, measuring the momentum of one and the position of the other with more precision than is allowed by the Heisenberg uncertainty principle. Now, this is interesting. She met Popper. Popper suggested doing this with a down-converted light, and they did it in Xi's lab, and the precision was greater than that allowed under the Heisenberg uncertainty principle. And then they tried to say, well, you're just dealing with one entity with a biphoton. But then it turns out even with like thermal light, you can actually get the correlations. And even there, you can do Popper's experiment, and it comes out in accordance with Popper's prediction and not Heisenberg's. And they still, no matter what, they just want to hang on to something from the past, Heisenberg's uncertainty principle.
So
It doesn't bother me a bit to say the problem is with the uncertainty principle.
So quantum mechanics is proved and disproved at the same time, but the same set of
Yeah, something like that. They just want to hang on to things. Same thing with wave particle dualism. You can show wave properties and particle properties in the same experiment. Yilmaz ran one like that. Aspect had an earlier one saying that you can't do both with the same experiment, and then Yilmaz had a special beam splitter, and he showed both with the same experiment. So much the worse for these dualities. I never liked dualities. The world ought to be one consistent position. You don't need dualities.
But what about double slit experiment? There is any explanation in frames of this explanation of all this, extra spaces, extra dimensions, extra what? I don't understand it.
I don't know that I do either, Vladimir. Certainly, if someone wants to clarify double slit, to me, you can have a split photon, one half going through one slit and the other half going through the other slit. You can try moves like that and see if you can get it to work. To me, that's a possibility.
I never believed that you have your half photon. How to get it? I don't know. How to see
with
it?
Elastic
How to measure it?
Yeah, with elastic scattering. So with a mirror, so when there's no absorption that occurs. So I think it happens all the time. But when you actually detect something, it involves absorption, and there you have to get the whole thing. So emission involves a whole discrete particle. Absorption involves a whole discrete particle, but what goes on in between may involve a lot of dividing and recombining and things like that. That's what I think actually happens. But it all involves fields, the electromagnetic field. I don't even think a photon exists apart from electromagnetic fields.
Let me ask you another question. These experiments were done only with lasers, or maybe with standard lamps, with standard.
Well, the initial ones,
black body
they were all
radiation,
done with
whatever,
lasers. But I know, and because the Defense Department was interested in doing this, they tried doing that with sunlight. And it turns out you can even get correlations using sunlight.
Use sunlight and they saw these correlations?
Yes.
Okay, it's
Thermal
very
light,
interesting.
But the initial ones were all done with lasers.
sometimes in experiments you get whatever you want. Maybe
There
this
can
is
be a
the point.
danger of that also, which is why you have to have different labs do some of these different things.
Oh my
But you're right.
goodness.
Any number of funny things can happen into that.
I don't believe it, especially fibers. I know how fibers works. Forget about it. There is so confusion. It's so difficult, fiber transmission. That's why whatever is happening during fiber transmission, I have no clue. Nobody knows.
You may be partly right there. I do know, at least they say they put it through fibers. And it's more than one lab that
I'm
does it.
very sorry, man. All my life I was optical guys. That's why, I have some experience.
Yeah, sure. I'm sure you do. Probably more. I'm sure it's more than I do. But yeah,
I'm so sorry. I'm very confused,
yeah,
especially with the double slit photons. They have a wavelengths, they have a mass particles, they can split. I don't know. Look, so many miracles I heard from you. I'm so sorry. It's not your miracles, maybe, but I'm very
yeah. I don't
confused.
believe in miracles either. So I think the physical world it exists without miracles, but it's odder than people think, and it does have things that are non-local.
You mentioned something quite interesting to me in the slightly not disconnected with the theory you're presenting or the experiment. You said that electric fields and magnetic fields exist. Say, for example, a hydrogen atom. There's a proton and electron, and so obviously the fields exist there, but outside the atom it appears neutral.
Yeah, it
So
appears neutral because they cancel each other out, the
yeah,
effects.
they cancel each other out from a great distance. So, but the corollary of that there exists is that there is, like in electromagnetic theory, a momentum and mass due to moving electric and magnetic fields. So the corollary is that some of the inertia you believe perhaps is due to the electrostatic fields and magnetic fields. Do you have any wider thoughts on that?
I don't know, but why don't I mention this with light? I think the fields exist with light even when you don't detect it because of destructive interference. The fields are still there. It's just they cancel out each other's effects, and they really magnify the effects with constructive interference.
Second, 1 second. Okay. Okay, continue.
Yeah. Okay.
You
So yeah,
name fields. Do you know that field is a classical notion?
yeah,
There
I
is
agree.
no field of any particle.
Well,
Field,
let's
by
be a little bit careful
definition,
here.
it's an ensemble of particles. It's something like medium, like something, liquid, air, whatever. Medium is medium. You cannot tell about medium.
Yeah, we may have a disagreement there. I'm
Yeah,
a realist about fields, and I think that the fields, I think light is transmitted through the fields with oscillating fields,
yeah.
uh, with wave packets.
I mean that's
If
my
you want
problem.
more details, take a look at my ebook, A Model of the Physical World. It's at my website, www.quantumrealism.net. Yeah, because that goes into more details, and I'm always trying to get it in better shape. So I
Yeah,
definitely appreciate feedback. And constructive is better than just saying it's nonsense because I don't learn anything if when anyone says something's nonsense.
All right, we're almost done here.
yeah.
All right, we'll continue on, I guess, in the next session.
Okay.
That's good. What's happening now?
Should be stopping anytime soon. I guess another 7 seconds.
Just less than 1 minute for in mine.
6, 5, 4, 3, 2, 1.
Well, yeah. All right, we're back here. Roger has given his request to record. Do we have any additional questions? I'm sure there's a lot to talk about here.
Is the talk finished? Can we thank the speaker? Because I was very impressed with that. Very good talk. So thanks.
I don't think Bob's here. I don't see
gone.
his. I think
Oh,
we
right.
lost Bob. Did anybody notice that his audio was fading in and out?
Yes, I noticed that.
And I think there's some issue with his computer. And because he didn't seem to be moving his mouth or getting closer or further away from the microphone when that happened. So I don't know what that was about. Okay.
It could have been just an internet connection thing.
Yeah, I thought about that too. I'm not really sure what that was. I thought it was kind of annoying when it first happened. I'm not sure what that's going to be like when on the recording. I'm not sure whether the recording was, it could be that you just would fade out and disappear, and that would be kind of annoying on the recording.
If it was the internet, then it probably won't show up on the recording.
Well, we'll see. We'll have to see.
Yeah.
Okay. Bob's not here. I don't know what happened to Bob. I had a little talk here. I wanted to continue on. I don't know if anybody wants to continue on with the discussion. I have a little bit of talk here about continuing my discussion about Einstein's mathematics. So we can continue with that if you're interested. I'm not sure I'm going to be able to squeeze it in.
Why not, Harry? But you might like to solicit if there are any comments on yesterday's proceedings at all, good, bad, or indifferent.
Okay, we got Bob back. Bob's got 2 windows here. Now he's got 3 windows.
He split.
Yeah.
Yes.
It's a good joke.
He got ran through a splitter.
I don't know what happened. I don't know. This is messing up for me.
Yeah, you got 3
Two
windows,
of them
Bob.
are probably opposite polarizations.
All right.
Well,
Can we see you? And
your voice is coming through twice as well because they're
Is it?
interfering.
okay, do we have any follow-up questions for Bob? Okay.
Do you think that superposition might be due to the moment of creation of the photon?
I think maybe I should close it. I'm going to close everything and start up again.
Yeah, you're getting echo from the multiple
Yeah, I'm
windows.
just going to close everything.
Multiverse.
Is that better?
You still have one other open.
Okay. I'll try. Yeah. Let's see.
Turn off the mic on the other. There we go.
Okay. Okay, now it's good.
Yeah.
Your video's gone.
Yeah, no video in this window.
There he is.
All right.
Okay, there we go. Okay. Okay, you had a question about superpositions?
Yeah.
Okay.
Do you think that superposition, the actions of it, are due to the creation of the photon or a pair of photons at the same time?
Yeah, well, I do know this much. I want to have, for a superposition of photons, I say that they are in different parallel subspaces. So one could be like vertically polarized in one subspace and horizontally polarized in the other subspace. And so that works for photons, I think, reasonably well. What gets a little bit tricky is, they talk about superpositions of atoms and things, or interfering atoms, and I don't know what to say there. So I can handle like interference and superpositions for light, I think, reasonably well with parallel subspaces.
Yeah, but do you think it's due to the moment of creation, the circumstances of that creation of those quasi particles, I call them?
Well, like in the down
they act
conversion
the way they do.
crystal, yeah, in the down conversion crystal, there is an event as far as I can see, that creates the signal in the idler photons. So there is a moment when that occurs. And so but I do think that one travels in one subspace and the other in another parallel subspace. That's the only way that I can see that they can have different polarizations, because I identify polarizations with these angles of these rotational waves. So one's rotating and the other's rotating orthogonally to which you can't have both occurring at the same time. But in one subspace, you can have one rotating one way and the other subspace, the other rotating orthogonally to it. If you have two subspaces.
Hmm.
I don't know enough about polarization, but with elliptically or circularly polarization, the polarization is changing all the time. What happens when that goes through a polarizer? Does the rotation still carry on, or so if at the moment it goes through the polarizer, the rotated polarization is aligned with the polarizer,
Yeah.
it goes through and then carries on rotating.
Well, no, I think the polarizer acts as a new source.
It doesn't act
And I
as a new
gave you
source.
that experiment. It's a real one where you do the two orthogonally polarized and no light gets through, and you put a third one in between the two at an angle, and then some light does go through. So I think each polarizer acts as a new source. It's not that it's acting like a filter and just lets some light through. I think it acts as a new source.
Right.
Yeah, I'm kind of that, when
Hmm.
you've talked about that before, and that kind of puzzles me. Yeah, it's
Yeah.
I'm going to have to, I would like to look into that a little more. So maybe if you could send me some references
Yeah, I
to,
can try to find some. There's something similar with the Stern-Gerlach experiment, except there you're dealing with like silver atoms and spin. But also there, it's like if you put a third thing in, you get something occurring that doesn't occur when one just cancels the other.
yeah. Now, if what you're saying is correct, that puts a lot of credence, and I guess you've already figured this out too. What Dowdy is saying about the re-emission.
Yeah, no, I agree with Dowdy on that. As far as I can see, I mean, the devil's in the details in a lot of this, and Dowdy knew a lot, but I've seen some people question some of his results, and sometimes I'm not sure who to believe. But yeah, to me, like the sun's corona, if you say that's what's bending light and not gravity, at least on the surface, that has a fair amount of plausibility to it.
Well, like you were saying, the relativity people and the people who have that are in the positions of running department chairmen and editors of journals, they sort of want to hold on to the pre-existing theories.
Oh,
And
absolutely. One saying that this is true all over the place. The status quo has a lot of inertia in anything, politics, you name it. Even if it's ridiculous what the status quo is, people don't want to. It takes an
Forgive
awful lot to change things.
forgive me if I'm wrong, but I believe that light bends around all objects that are observed out in space. All bodies in space bend light. Correct?
Well, here's what the question is: whether they're in a complete vacuum or not. Now, for Dowdy's theory to work, you need something like a plasma, a corona, or something else in the surrounding
Well,
region.
I believe an atmosphere would constitute as a plasma um, uh, it would constitute as a plasma. It would do the same thing by bending light around an object.
Yeah, refraction.
And yeah, and we see that on the moon. We see that on planets, that these things bend the light around them.
Yeah, and
And
all of
it's
these
not gravity,
presumably
it's
aren't perfect
plasma.
vacuums. Yeah,
Yeah,
yeah, they probably have a
it's
very
not
weak
gravity, it's
atmosphere.
plasma that's doing it. I
Well,
maintain that 100%.
yeah,
Yeah,
that may be so, but for my part, I see no reason to depart from classical Newtonian theory, which ascribes the bending of light to the gravitational interaction. And you can work out the equations and you get this deflection. It happens to be half the value that Einstein predicts. And the experiments indeed haven't distinguished between the two. But if I could just come back to another point on the EPR, just very briefly, just a general question, Bob. I thought the EPR paradox was designed basically to indicate the incompleteness of quantum theory. That it couldn't be a complete theory.
That's what Einstein, Podolsky, and Rosen. That's what they said. Yes.
So, are you saying? Are you trying to save some of the quantum ideas, or are you resolving the paradox?
Well, I'm trying to save realism, but I'm willing to admit non-locality. So they're global effects.
You want to explain what non-locality means?
Well, at a distance, basically something spread out like between these two detectors, which may be miles apart, where what happens at one is affecting, well, to me, it's actually a joint effect between the two. Like joint, there is such a thing as two photon absorption. So it's joint. They call it correlated two photon absorption here. So both are discrete amounts, but it's drawn from different regions, the energy fields.
But you haven't
So it's a
ruled anything
non-local
in or out. So, for example, my provisional explanation that there is a field interaction traveling at maybe orders of magnitude greater than the speed of light, you haven't ruled that out. You seem to be open with regard to the causes of non-locality.
Possibly, but have to be extremely fast to account for some of these experiments. Like I said, the Chinese one with a satellite, which would be, it's, I don't know how high, probably 100 miles up there, and within like 10 to the minus 8 seconds or so, which that is fast.
Things maybe millions of light years away, which seem to, have some effect. So that would be the same thing.
Yeah.
Between Earth and satellite, there is ionosphere. What about this plasma? How they took into account?
That's a good question. I don't completely understand it. Like, okay, you're sending light through the atmosphere, and how that atmosphere isn't messing up the light. That's not a bad question, Vladimir. And
there is no vacuum. There is no vacuum. Forget about it. That's why all these experiments in space, in any space, depends on composition of this cosmic medium. That's it. And the most important, of course, plasma. And how they took into account this plasma, I have no clue.
Well, I guess a big question I have, did they use light beams or radio waves?
I believe I've actually got the paper. I believe it was
All right,
light,
why don't you,
I have the paper.
Why don't you put that out so some of these things for us to look at? I'm sure people. I know that you did have lots of references you did have references at the bottom of your slides.
Yeah, I can. It has a huge number of authors. This Chinese one. If you like, I can run over and get it.
That's okay. Just
okay.
All right. Any other? Are we done with that? I guess we have some questions about that. When you mentioned that at the beginning, I thought to myself, radio waves. But
what would help, Harry, is after this presentation is over, send me an email with as specific questions like that as you can, and I'll try to look up the ones that you want, and I can give you references.
I've got your website up. So which is the paper that's most relevant to what you've spoken about today? Because there's a whole list of them.
With respect to what?
What you've spoken about today.
Oh, well, it's on entanglement, which is in my chapter on light. I think there's a whole section on entanglement. I think that's chapter 3.
Am I looking at the wrong page then? Because I'm looking at a page with lots of downloads, about 8 or 9. 2, 4, 6. 7.
It's the model of the physical world.
Oh, yeah, the top one. Okay.
Yeah, the top one, yeah.
Yeah.
Okay,
right.
any other questions for Bob? Okay, you
Yeah,
want to
send me
talk?
those questions about references, and I'd be happy, and I can give you emails of people who know some of this better than I do.
All right.
All right,
Um,
just one more. Are there future plans for more experiments in this domain, or has it all been wrapped up and
The one I've thought of, assuming she is right about being a negative result with the particle cell, because particle cell will work off of a phase shift. There are such things as mechanical choppers. You can actually get a mechanical chopper rotating disc that goes as fast as 100 kilohertz. Those are commercially available. Now, you need light to go a great distance there. The real truth is this: there's a laser reflector on the moon. Niels Armstrong, they left one up there. There's some others up there. You send down converted light to the moon and back, then you could use a mechanical chopper. See what would happen. I'm not sure you
and
could get light that far, but
a Kerr cell, is that not suitable? That's is that a Pockle cell? What is a Kerr cell? That's chopper. I
well, I mean,
can't remember.
well, you see, the Paco cell, that's one that they use. That works off a phase shift. But you could say there you're just dealing with interference and you're not really blocking something. As I was saying, with interference, maybe the fields are still there, they're just not being blocked. But with a mechanical chopper, you've actually got something solid doing the blocking, which I think would be preferable. But the trick is, either send light far enough or to get your chopper fast enough that with light you can still do it.
Okay. Thank
okay,
you very much.
Yeah, sure.
Nice.
And if anyone has questions, feel free. I mean, to send me an email. I'd like to get some of this, get more people interested in moving, and I'm always trying to get my theory better. So I definitely welcome email correspondences, and I find email correspondences, like I've noticed some of the ones going on, they just go on forever, and you get personal attacks and things, and it's just not helpful. But a directed one on some of these issues, and just getting the people who are really have an interest in it talking to each other, I think that definitely could be helpful.
okay, I got a question for James. Do you want me to add you to the mailing list for the Sunday morning?
Yes, why not? But I'm not always available on Sunday. But
All
yeah,
right.
yeah.
Okay,
But
I'll do
yes.
that.
Did you get a request from Jeff Boyer for the same thing, Harry?
Yeah, I put him on the list and I sent him the links for today's meeting.
You don't have to attend, James, every time, but once you're on the list, you know that it's taking place.
Yeah, I've
Okay,
seen one or two of them.
Ian, you asked about the presentation from yesterday. Anybody have any comments or questions about that? We've got, I guess we got about 20 minutes left.
I was just thinking about this after the lecture, and if Jeff had been here, it might have been a bit difficult. Well, he probably would have answered this, but you see, in a way, unless I'm wrong, it's not only GR and SR which is, being attacked by his fundamental reassessment of this differential business, but it's every theory which is based on, infinitesimal calculus. He was saying, well, look, this takes the base out of GR and SR, but he could easily have had the lecturer saying this takes the base out of many of the major theories of physics which use analytical methods based on differentials. It's just a thought occurred to me later on.
Yes, you could look at it
Right.
that way. Maybe that makes binary mechanics look good now.
Well, yeah, like the basically all the math you need is the and, not, and function and binary numbers. However, this calculus in terms of differentiation and integration is still useful, in my opinion, to describe what's going on with aggregates of the quanta that binary mechanics describes, or the ensembles that Vladimir talks about. So that that's when I was a young guy, that was just called statistical mechanics, and that will always have a place, I think.
I mentioned also Berkeley's critique of the differentials, and it seemed to be attacking it and saying you could be leading anywhere. But another interpretation of what he said is that it seems illogical because you're dividing by zero, which is a no-no. But you're saying, well, you're letting the difference go down. So, and it's all right. You get the correct result. Berkeley exceeds to that. So he's saying you're taking it on trust from, say, the mathematicians, the experts, and then you're getting the correct result. And therefore he's saying, well, perhaps you should take on trust, maybe from the theologians, the idea about how the design of the universe came about. It seems to be illogical, but take that on trust and then see whether it gives you a correct result as well, that the world is capable of order and interpretation. So the reason I mention that is it can be taken that Berkeley was critiquing this and saying it's the first step to atheism. But he also perhaps was saying that it's something one might take on trust because it gives the right answers at the end of the day. He was a mathematician himself.
So that would be a critique of physics.
It would be a critique of physics using the traditional mathematical tools, yes.
Yeah, but isn't their whole philosophy based on the fact that they do an experiment and the experiment proves the theory, therefore the theory is correct?
Yes, and that might be our critique, surely. But I think he might be saying, yes, he might be applauding that. Perhaps you should do that, provided the results are.
Yeah, I think what Bob has presented to us today is that in quantum mechanics, they seem to have a theory, but they don't really have an interpretation of the theory. So they
have competing interpretations, but
well, a unique interpretation or a one and only. So that means that nature could have multiple different realities as far as interpretations are concerned, which to me is sort of disturbing, but that also comes out of special relativity, I think, because
I don't think I'd want to say that, but it's arrogance to say that we know the way the world actually is.
You're decrying sort of the miraculous explanation. I think might militate against that. Your bias might be not to accept these sort of multiple simultaneous.
Well, if you want to bring in Berkeley brought in God for all of this.
Yeah. Of course he did, yeah.
But also, like with calculus, you can say it isn't really infinitesimal, as you can talk about limits of and ratios, and as the limit gets closer and closer to zero, the ratio approximates a derivative. So you don't have to actually have infinitesimals.
Yeah, that was one of the issues that I'm not really sure that Jeff answered that issue. It's really basically they take the limit as the functions get smaller, the differential.
Yeah, but that's 19th century math. That isn't Newton. Newton did talk about infinitesimals, and I think Berkeley he was directing his criticism.
Yes, Newton he started it.
But see, the Leibniz notation of the dy and dx is what we use every day. And it's very illustrative. You see exactly what's happening. It's a ratio. But it's basically starting from a finite difference, delta y over delta x, and then it's coming to that limit. And in modern analysis, I think I've done it myself, you tend just to use dx and dy. Like maybe if you had a diagram, a geometrical diagram, you'd have delta x and delta y, and then you'd only write the formula in the limit at dx and dy. But you actually have mechanics books now which have little elements which are called dx and dy. You don't make distinctions between them. Whereas with the Newtonian notation, he would just maybe have a dot on top of the variable to show its differentiation.
Or time derivative.
Yeah, well, that's what we use nowadays. When we have very complicated differential equations for time derivatives, we put a dot on top. But I think Newton did that for all derivatives. He didn't have the dx.
You may be right. You may be right. You may know something I don't there.
Yeah, yeah. So it's just interesting to look at it that way. But Jeff was really maybe quite fundamentally objecting to this infinitesimal
I think
business.
I didn't quite understand it, but I think he was more relating to in general relativity, you're changing length scales at the same time as you're taking differentials. And I think he wasn't so much arguing, because he said this is all right in the elastic theory, stress strain, etc., in a conventional and a solid analysis. But when you're doing changing all the dimensions of everything with time scales, length scales, and such, you're bringing in errors which you should account for. And he didn't say you could account for them, but he just said that they weren't accounted for. So
I think what you're pointing to is whether or not we ought to believe in time dilation and length contraction.
I do believe in that there's a different time going on slightly in a different frame, but I don't believe in using more than one officer standard. So you want to encompass their slightly different experience into the whole arrangement using one standard or unit standards definitions, basically. So you don't say that there's two times going on at the same time, but there's an effect. There's effect on their frame which is causing the difference.
Well, that's what I was saying earlier about the non-uniqueness of reality and special relativity. Special relativity says reality is not unique because you have different times and different lengths going at the same time. So two different observers see two different physical realities.
Or it's not realist in terms of the definitions used by Bob today.
Right. Yeah. Well, I think the issue is that quantum mechanics also has that multi-world thing, which I'm not sure whether that comes out of quantum mechanics or whether that comes out of special relativity or whether it's an attempt to mesh the two together.
Well, normal quantum
in my view, it comes out of modern metaphysics. I mean, it's the modern philosophy of things, which is not so deterministic. And it's come both to special relativity and into quantum mechanics.
Multiple universes, multiple dimensions.
Yes,
that's what he's talking about. And he's right. That is modern. It's only really started up since the 60s and 70s. And people believe the TV instead of scientists.
Yeah. Well, the multi-world one, that was Hugh Everett. I think his original paper, I think, was late 50s.
Yeah, it would. But did that come out of quantum mechanics, or did that come out of? I think that came out of quantum mechanics.
Yeah, it did. Yeah.
And that had to do, I think, with the idea that there's of the uncertainty principle, or is that not correct? It had something to do.
At least superpositions.
I was gonna suggest that it came from superposition.
But the point is that a hint of something like that from quantum mechanics or whatever then is extrapolated to some media presentation, and then that feeds back into science itself and expands the whole thing to something that perhaps it never meant in the first place.
Well, Bob, would you say that the multi-worlds interpretation is or is not realism?
It's realism, and mine in a way is a little bit like that because I have all these parallel subspaces. But for
Goodness.
Everett's version, it's all the possibilities have their own world. Uh, it's an enormous number of worlds you get into there. I suppose there probably is both a realist and a non-realist version of it. The non-realist says it's a calculating device. The realist version says they all exist. Would be an enormous number.
Well, it's kind of
If
hard to
every
accept.
possibility is actually happening at this
Right.
time, and it's observer dependent because we can only observe what's happening here, but
Yeah.
every other possibility is existing in some other.
Yeah. And everything time there's something like a measurement, it splits the universe in two and stuff.
So that would be a non-uniqueness of the world. The world is not unique. It's
Yeah, I don't know. It's a real strange one, but evidently it gives good predictions. And it's not saying that any one world is any more primitive than another one.
so you have multiple realities, but you can't determine what reality you're in, or
I guess. I don't know.
I just find it hard to grasp the idea that reality is not unique, that there are multiple realities.
I agree with you, Harry. I think there's one, but it maybe it kind of has odd properties, which is fine with me so long as they're consistent. I'm
Well,
satisfied the universe is a lot odder than we ordinarily think of it as being, but
maybe it's not that the universe has odd properties, but our theories do.
maybe. I'd always like to simplify mine, but the trick is to get it also to be consistent with known experimental results.
I mean, is JBS Haldane's dictum that the universe, that he suspected the universe is not only queerer than we know, but it was queerer than we can know.
Maybe some people say that we can't really, our minds aren't equipped for understanding the way the world is. Who knows? I make an attempt, but
Can I ask you one question?
sure.
Time is absolute or not?
I think there's absolute simultaneity.
Okay. I'm asking about time in the whole universe, the same time or different time?
Well, I think there's absolute simultaneity for the whole universe. And if you want to call that time, maybe.
Another vote for binary mechanics. I might
Fine.
point out that with the sort of quantization of length that Jeff talked about yesterday in his infinitesimal elements and the three postulates of the quantization of energy, space, and time in binary mechanics, that in principle, the equations of quantum mechanics fail. Because if these three items are in fact quantized, Jeff talked about one yesterday as a possibility, it means that results of quantum mechanic equations may more often than not be referring to a position that in fact does not even exist, or a time that does not exist because it is somewhere in between the single time tick in a quantized time regimen, or a single space quanta tick in a length measurement. So in principle, the equations of quantum mechanics are not able to represent the kind of realism that we need in physics, is a point to think about.
Mhm.
Let me tell you my opinion about this. First of all the equations, what we have in our physics, they are valid only for classical physics. In quantum physics, there is no length, there is no space, there is no time, there is nothing. I
What is your
told you
reference
many
for
times,
that?
you can introduce these notions, even time, space, and all this stuff, only when you have your classical physics and you have your cosmic medium. The characteristics of the cosmic medium, it's exactly the expression of time, space, and all this stuff. That's why all these Schrödinger equations, all this stuff, they are absolutely wrong. Absolutely, because there is in quantum physics, there is no such notions even. Space, time, and all these equations, especially when you have your derivative in the Schrödinger equation. It's all this, story. It's totally wrong, totally wrong. And what is important, I watched yesterday the video by Penrose. He's criticizing this quantum physics, and he told it doesn't work for him. It's wrong for him. And Penrose, he has some knowledge about the physics.
He
sorry.
seems to have done a U-turn, actually, in recent times. Penrose has. He's changed his views about all these things.
Yes, especially about quantum physics. He told me he's incomplete. He's doesn't work for him right now. That's why, guys, quantum physics is a totally different story. It's a single object. For single object, you cannot tell about time, space, and all this stuff. James, it doesn't matter. What is your length? Yesterday, it was some question about your value of this tick of length. What is the value of it? What is the number?
Well, in the Keene scale, it is
0.67 femtometers. Is that what you said?
No, femtometers or femtocentimeters, it's a totally different story. I heard yesterday.
FM, femtometers.
Femtometers, and how
That's
much?
10 to the minus 15 meters.
I know what does it mean. And how many femtometers in your length?
Well, 0.67.
0.6.
And that's an empirically determined value based upon reverse engineering of the secondary constants, which are the speed of light, Planck's constant, electric charge, electron rest mass, and the speed of light, if I didn't mention that already. So
right,
this is an empirical value in binary mechanics. It's not just something dreamed up out of the air. It's based upon
and let me tell you about the
measurements.
empirical value. I got it based on the experiments of 19th century. It's a Rydberg equation. It is, a value of electrodynamic constant. It is a value of Planck constant based on the black body radiation. And the last one is ratio of mass electron to mass of proton. Based on these 4 experimentally measured values, I calculated the basic size unit 10 to the minus 14 meters, 14, not less than 14. What is important? Cosmic medium, you can start working with it. It is 10 to the minus 10 meters. 10 to the minus 10. Compare your 10 to the minus 16 to 10 to the minus 10. You can start talking about this space and time.
All right.
Because without cosmic medium, it doesn't work.
All right, I'm going to finish up here. Bob, do you want to have any comments to make at the end? You got about a minute.
I don't know if there's really a specific comment, but I am interested in, getting some feedback and trying to get what I have to say in better shape. So if anyone would like to start up an email correspondence, and I think it's best off directed at a fairly small number rather than a huge number of people. But my email is robert.e.french@gmail.com, or take again a look at my ebook, A Model of the Physical World, at my website, www.quantumrealism.net, because I am interested in feedback and a discussion.
Bob, this was a very interesting presentation today. Thank you, sir.
Yeah. Okay.
All right.